So the purpose of this interview is just so we can gather some answers to questions that we can't really find on Google or anything like that. So, do you have any questions or comments before we start?
So are we just talking about tornadoes or any kind of science project that we do?
Um, the CSWR and tornadoes in general. Like we have parts about the CSWR, the Dows, and just some other questions.
Well, again, most of what CSWR does is not tornadoes. That's why I was asking. The
Yeah.
hurricanes,
I think
the winter storms.
this is more tornado oriented. All right, our first question is, how successful are data collection attempts? Is there a certain must-have scenario for getting data?
So, success rate for tornado missions varies a lot. It depends on our goals and whether or not those missions are hard. And so when we go out and try to collect data, let's say get some radar data in a tornado, that's relatively easy. We can be a couple miles from a tornado. We could be north of us or south of us. It could be crossing a road, not crossing a road. And so it's easier, if a tornado occurs near us, we probably can get some data. There are other missions which are much more complicated. If we're trying to get what we call dual or multiple Doppler, it means we have to have more than just one radar scanning through that tornado. We need to look at it from two different directions and synchronize and have the radars the right distance apart and have the tornado kind of between us. Well, that's harder because it's harder to position that in just the right way. If we're also trying to get radar data combined with in situ data, let's say pod data or something where the tornado is actually crossing an anemometer at the surface, that's also hard because we need, it's hard to get the pod data, it's hard to get the radar data, and the chance of getting both of them at the same time is even harder. So our success rate depends a lot on essentially the degree of difficulty of what the mission is.
All right. During your time working with Sean Casey, would you say you collected more data from the pod teams or the TIVs?
Well, we collected more data with the pods because first of all, we have a lot of pods. We were deploying over a dozen pods. So we would get them out there a lot and get data from them. However, some of the most high value data was from the TIVs. Because huge advantage there is that we put down our pods and the tornado hits them or misses them, and we put down arrays of pods and have the tornado slip right between them. We put down arrays of pods and have the tornado turn. The advantage with the TIV is that that may still happen, but since there's a human in there, the driver can adjust and get it in a better position.
All right. What do you think was the best or worst CSWR mission you've experienced?
Well, it's very hard for me to define best or worst. It's more of a multi-dimensional scoring. On the one hand, there's best and worst in terms of getting valuable scientific data. On the other, there's whether it's very satisfying or interesting, or whether it was just a miserable experience because something broke, something like that. So it felt very good. On a personal level, probably one of the best missions was the first time we made really good maps in a tornado. So way back in 1995 in Dimmitt, Texas. Now, is that our best data set now? No, but I remember that day because on that day we got close to a tornado. The radar was working. It was brand new. We scanned through the tornado and saw things that nobody had ever seen before. So it was a really great big moment of discovery there. So it was very exciting. Right in real time, we knew that we'd seen something really spectacularly, that we had data that could really push science forward. So that was probably the best day for me. Bad days, boy, there's a lot of them. I mean, we've been out on probably thousands of, over 1,000 tornado chases. And there are days where things just break. The radars break. There's a lot of days where we forecast wrong. There's a lot of days where the radar works, we forecast right, but we just can't get the data we want because tornadoes are happening in areas where there's hills or trees, or it's just too difficult logistically. So there's a lot of days which have frustration to them. The key to what we do is we just go out there year after year, and we keep plugging away at it. We know we can't you were asking about the success rates of tornadoes, or success rates of the missions. Well, on any given day, it's probably less than 50-50 that we're going to get a really good scientific data set. But we keep plugging away at it. Our standards have gotten higher. So that great success back in 1995, today I'd go, yet another tornado. We have maps of the winds in tornadoes, 200 some tornadoes. So getting another one wouldn't feel nearly as amazing as it was when we got the first one. Now we're trying to do much more difficult integrated data sets. We're trying to get multiple radars. We're trying to get pods and other instrumentations in and near the tornadoes. We're trying with our mobile mesonets to get slices around them. We're trying to launch airborne instruments, balloons and things into the storms to try to get thermodynamic data aloft. So we're trying much more difficult missions. I would say if we are able to succeed in getting all those integrated in one data set, that's what we're aspiring to. And if we ever get those all in one storm, good mature storm, that will be our best data set when that happens.
There's a lot of information online about the Vortex 2 mission. Is there any place that we could possibly find information about the original Vortex mission?
Vortex 1?
Yeah.
Right. So, of course, there was much less web back then. I mean, there was some, but not a lot of stuff was happening online. Now, if you've Googled around, that's probably where you'd have to get the information. There was a article about it in the bulletin of the American Meteorological Society. You could read that. Otherwise, just Googling would tell you information. You could certainly look for publications. I mean, we published data from it. This Emmett tornado I was talking about from 1995, that was during Vortex 1. So there's results from scientific publications like that. But you're just not going to find the same richness of information that you do in the modern era of projects. Vortex 1 was 25 years ago. That's a long time in the history of the web.
Are there any new experiments we should keep an eye out for, and will any be taking place out of the country, like in Canada or Mexico or anything?
There are projects proposed to take place in different areas. There is a project called Wintry Mix, which is being proposed to happen in Canada near the Montreal area in 2022, for example. But we don't know if that will happen. There are many projects that are proposed, but only some of them move forward. Only some of them really, there's more projects, more ideas that scientists have than there's money to go around, basically, or resources to do them. So a lot of projects get proposed and a few of those move forward. So Wintry Mix, it seems like an interesting project for 2022. We're also planning a project, I think it's called Crabs, for 2022, maybe 2023 in New England, looking at winter storms. That's not out of the country, the edge of the country. So there are future projects like that. We have possibilities of future tornado projects and other types of projects, but we just don't know what's going to happen. This summer and fall, if there are hurricanes, we're likely in a kind of ad hoc way to target the hurricanes. But that just depends on significant hurricanes making landfall. And years there are multiple storms that make landfall, and some years there are zero. And we really can't tell this year whether this year is going to be a good year or bad year, because a good year for landfalls is a bad year for people who live in those areas. But whether or not it will be a year where there are multiple landfalls.
So we know that the Cow DAO is the latest installment in the Seas to Be Our Fleet. Do you have any specific plans with Cow that the other DAOs can accomplish?
Well, the Cow is a C-band radar. It uses longer wavelength radar, microwave. So it's much better for penetrating through heavy precipitation, for mapping out the complete storm. And it's better for collecting dual polarization, microphysics information there, if we're trying to really study hail and rain rates. So that radar has been proposed for different projects, and we're still waiting. As you can imagine, this year, a lot of stuff is in chaos and getting delayed. So there are projects to study precipitation down in Texas. There are projects in the southeast to look at tornadoes. There are various projects. This Wintry Mix project has been proposed to use that radar. So we would like to use it for a variety of different projects because it has capabilities that the Dows don't. So the Dows have 8-foot antennas. We can chase around with them. We can do tornado work. We can move them around, deploy them in a few minutes. But there are a lot of, and so that's great for tornadoes or tornado chasing. But for projects where you can park the radar somewhere for a few days at a time, the COW has some excellent capabilities. It still has a very, very narrow beam. It can see through the heavy rain and hail better, but it's just not as nimble as the Dows. So we basically mix and match and customize depending on the project.
So we know that the CSWR has gone through a lot of different radars and a lot of different vehicles. Is there a specific Dow that broke down a lot?
Well, the first one, Dow 1, that was our prototype system. We basically borrowed a box van, an Econoline van, and cut the back off and loaded it up with thousands of pounds of radar pedestal and antenna and computer racks and a generator and fuel and hydraulics. It was very heavily loaded. It was an old van to begin with. It was constantly breaking. We had to have a support car follow it just for safety reasons because we were worried it would break down when a tornado was heading towards it. So it was basically a rescue vehicle. The idea was if the Dow 1 broke down, the crew would grab our disc because we wanted our data, grab our disc and run out. You know, they always say on an airplane, you know, don't grab your luggage before you leave. Our plan was to at least grab the disc and run if we had to. But that was breaking down all the time. We basically had zero money to buy a new vehicle and customize it correctly because we were prototyping. You know, the idea of having a mobile radar was quite a new concept and a lot of skeptics at the time. So we basically built it really on a shoestring, literally a lot of duct tape and things like that, keeping it together. So yeah, it broke down on many missions.
Are there any specific storms that warranted the most successful Dow deployments?
Were or were not?
Were there any storms?
Sure, I think any storm that had really groundbreaking data. I mentioned that Dimmitt one back in 1995, where we made the first maps ever of tornado winds. Those were really exciting. In 1999, during the May 3rd Oklahoma outbreak, there were two different storms which had really interesting data. One where we mapped winds of 300 miles an hour. Another one where we made the first maps of really good maps of multiple vortex structure. There was a minor storm in 2007, which for us was excellent scientifically, even though it's a very unknown tornado up in Kiefer, Oklahoma, because it was the first time ever that we managed to get two radars triangulating on the same tornado, and we're able to retrieve the vector winds in those tornadoes. During Vortex 2 in Goshen County, Wyoming, 2009, was one of the best observed tornadoes ever. So that was an excellent data set, just looking at the entire life history of a tornado. So that's a very well documented tornado. So really good data there. One thing we've been trying to move away from, however, as our science matures, are these studies of individual storms, like what I've just been mentioning. And we've been trying to basically advance beyond that and move to a standard that other sciences have, where you really try to study a class of objects. You can imagine, let's say you were doing a study of some kind of birds, right? You were doing an eagle study. Well, you wouldn't go and study one eagle, right? You wouldn't even go and study a couple eagles. You'd probably try to look at hundreds of them or thousands of them, so you can understand how big they were, you know, how many kids they had, you know, how many eggs they lay, what their terrain. You try to study them as a species. And so what we're trying to do now is move beyond these individual case studies. There's the Dimmitt tornado, there's the May 3rd tornado, there's the El Reno tornado, and move on to look at the species of tornadoes. So in fact, we just submitted a paper yesterday, which did an analysis of 120 different tornadoes that we'd analyzed, the first 120 or so tornadoes that we'd seen in the first decade of the Dows collecting data. And we tried to look at what their the distribution of intensities were. If I asked you now, how strong is the average tornado, or how large is the average tornado? Couldn't really answer that question. And the fact is, until this study of our 120 tornadoes, scientists couldn't answer that question either. We have damage surveys that say most tornadoes are F0. And we have damage surveys that say most tornadoes are less than 50 meters across. Well, that's false. They're not. Our study reveals that most tornadoes have winds that are EF2, EF3 intensity on the average. Our study reveals that 20% of tornadoes could cause EF4, EF5 damage if they crossed into towns. Our study reveals that the average diameter of tornadoes is 300 meters, about 1,000 feet across. So they're much stronger and larger than previously thought.
Yeah. So you're looking at the big picture rather than the individual little ingredients.
Well, we're trying to look at the species, the phenomenon of tornadoes, not individual ones. Again, imagine you're doing a medical study of humans or something. You were Martians and you had to study humans. Well, you probably wouldn't get one human, put him in a lab and study him. You'd probably try to take pictures from space and say, hey, there's big ones and small ones and old ones and young ones and white ones and brown ones and long-haired ones and short-haired ones. There's all sorts of different kinds of humans, right? Yeah. And the same is true of tornadoes as a species. There's a great variety of them. And if you just looked at one or even a few, you might not really understand the species. So we are trying to understand the species by moving our studies from case studies to multiple examinations, analyses of multiple tornadoes at a time. And so that's one of our big breakthroughs right now. Now, to do that, you still have to collect lots of individual tornado data by chasing. We're not a laboratory science, so we can't, it's not like looking at mice in a lab or bacteria in a dish. We have to actually go out there and chase them, capture them, to study tornadoes in the wild. So that's why we keep doing that. But our goal is not to look at sort of my favorite tornado type of papers, but to really get into these multi-case studies. Our friends, I have friends in physics who they used to call me a stamp collector, because they'd say, yeah, your papers, they sort of read like stamp collecting. Here's a stamp and there's a stamp, sort of your favorite stamps. Whereas the physicists would go and say, we're not going to study my favorite electron. We're studying electrons as a phenomenon, as a species.
So we know that a lot of weather computers and computers for forecasting use Linux. Do the Dow computers use Windows or Linux primarily?
Well, we use both. And I am completely nonpartisan when it comes to operating systems, whatever gets the job done. When we built the first Dow, that Dow 1, that used DOS, the old system, and it was just because it was super easy, it was super dumb. When the computers crashed, when the generator failed, it would boot up in a few seconds. So it was just simple and great. As we've gotten more advanced with our systems, we have a bunch of Windows systems because a lot of very useful tools are written in for Windows. 90-some% of all computers in the world use Windows. So if we want to use navigational systems or various kind of tracking or ingesting of weather data, things like that, a lot of those use Windows. However, some of our specialized software that operates our signal processing for the radars, that's using different flavors of Linux. And we'll use Ubuntu, and we'll use Red Hat Linux. We'll use CentOS. We use different flavors of Linux. I'm so old, I still call it Unix, but basically different flavors of the Linux of Unix.
So how big do you think like a chunk of data, like say if you're chasing for a day and you got all the data that you needed for that day, how big do you think would those files be?
Well, when the DAOs are operating, they collect probably about 200 gigabytes an hour. So it depends on how many hours we're operational. So if we're up for several, and there's multiple radars, of course. So it's easy for us if we're not chasing tornadoes. If we're parked for all day collecting data in something, we can collect several terabytes a day. In tornado chasing, usually it's less than a terabyte because usually we're not operating all the radars for that long. We'll maybe park them for half an hour or an hour to collect some data in a tornado. And maybe only 1, 2, 3 radars are collecting the data. So usually less than a terabyte, but in other projects we're sometimes collecting multiple terabytes. The pods and other weather station data is almost zero. I mean, weather balloons, pods, those things, they're just collecting megabytes or something, very, very small amounts of data. It's the radar data that's really biggie.
What, in your opinion, would be the most interesting thing in your normal day-to-day job?
I like seeing things and discovering things that have never been seen before. And that doesn't happen day to day. But on the special days for me is when I've made the first map of a tornado, seen these multiple vortices, or mapped out the downdrafts or updrafts in the tornadoes, or watched something happen that has never happened before. It's a new discovery. It's probably exercising the same kind of brain cells that explorers did hundreds of years ago when they landed on a new island or continent or river. So I'm not seeing any new continents, but I'm seeing fresh things. And that moment of discovery of wow is really exciting for me. And that can be right in the field when we see something on the screen live, or it can be later when we've started to analyze the data and we say, whoa, look what was in there. We didn't see it at the time, but now we're looking the next day at the data, or even the next month. We're seeing some new phenomenon that's never been seen before. Sometimes it might have been something we suspected was there, but sometimes they're total surprises. The first time we ever took DAOs to a hurricane, we saw a new phenomenon that we weren't expecting, that initially we thought maybe it was the radar being broken. We spent a long time going through making sure it wasn't just something wrong in the data, but we saw these big streaks in the wind, these organized linear streaks in the wind, because the wind in a hurricane doesn't just blow horizontally, it goes like a corkscrew. So we discovered something unexpected, and that's what gets me up in the morning. It's really fun to do that kind of thing. Very rewarding.
Do you prefer the engineering or meteorological aspect of chasing? Because we know that you're always coming up with new ideas. So is it the engineering parts or meteorological aspect which drives you to continue storm chasing?
So I love designing and building things and tinkering. I have up in my office this plaque I was given when I graduated elementary school. I graduated 6th grade, and I went to this little teeny school in Philly. And it basically is all about me wanting to be chief engineer. They sort of gave their students long leashes then, and I was chief engineer of this big basement renovation, So I've always liked building things, designing things. So that really is fun for me. And the fact that I can go and build DAOs and do stuff like that. People ask, what's my hobby? And it's like, well, my hobby is my job, because if I have a new cool idea, like a radar or these pods or some variety of something, I can just build it. Hopefully use it for my day job. So that's really exciting. But as I was saying before, I think they're really tools. So I do like building them. They're fun, but the more in-depth, rewarding thing for me is the meteorology. It's the discovery. It's seeing new things, discovering new things, pushing knowledge forward. Is really what gives me my more deep enjoyment, deep rewards. What I've done in my career and what's been successful for me is really straddling, keeping one foot in each of those. I'm not a trained engineer. My PhD is in meteorology. But I know enough engineering and have enough practical sense of what's going to work, what's going to be pushing the envelope, but not too far, that I can push forward, facilitate these new engineering advances. But I also, because I have the other foot in meteorology, they're always focused. If I'm just an engineer, I might be building some exotic engineering things, may or may not be of most use. But not only am I the creator of the DAOs, but I'm also their main customer. So I build them so they can do really useful things for my meteorology hat. So, you know, my engineer hat's on in the morning and my meteorology hat's on in the afternoon. And really combining those has been what's made the Dow program successful.
We know Storm Chasers was like a long time ago, and did the show Storm Chasers negatively or positively impact the CSWR in any way?
I think Storm Chasers was a good influence. I mean, there's positive and negative things about human, and there's definitely a different culture and different priorities between a television entertainment endeavor and a scientific research endeavor. But I think we were able to mesh those pretty well. Discovery funded our scientific missions, which are expensive. As you can imagine, getting multiple radars out there and 20 crew and all these pods, and there's salaries and hotels and lots of gas money. So it's an expensive endeavor. And so get funding from various scientific agencies, but they can't fund enough, and they can't fund it every year. So we can't get enough data to push our science forward through the formal government agency routes. So one of the great things about working with the television was it provided a way to fund the science and support the science. So that helped CSWR directly. I think people think that the PR helped us, and probably not really so much directly. I mean, it's not like the key for us is being able to do science. And to do science, we need to have good creative scientific ideas, and we need the means to execute them. So we need good, smart people, we need brains, but frankly, we need dollars. You know, the brains and dollars are what makes science happen. And so partnering with non-traditional sources like Discovery for Storm Chasers. We had partnered with National Geographic before that for some different documentary shows, and they supported some missions into hurricanes and tornadoes. So partnering with those non-traditional sources of funding certainly helped CSWR.
How did you first meet Sean Casey? We know that he was a big part in your research mission back when Storm Chasers was airing. Did you meet him from the Discovery Channel crew, or did you just kind of find out about him?
No. We knew Sean from before Discovery. Prior to that, Sean basically was trying to collect IMAX footage for a IMAX film called Forces of Nature. So he was basically trying to collect imagery of tornadoes, of volcanoes, and of earthquakes. Those were his three forces of nature. So he basically came out with a small crew and a pickup truck that they modified, and they basically followed us, collecting some footage of us, but also a lot of the tornadoes themselves. Then there was a phase where they were working with National Geographic, and so basically Sean's team and my team worked on a tornado documentary for National Geographic, and then there was Sean and some of his colleagues, friends, put together an idea that maybe they could do something more than just a documentary. They could do this episodic show, which got called Storm Chasers. And then they approached Discovery to do that. So we had not known Sean for years before Storm Chasers, both when he was on his own doing IMAX filming, then through National Geographic, with National Geographic, then through Storm Chasers.
And I found out that there was this scientist named Dr. Josh Wurman who seemed to be very active out in the field. So I called him up. I said, "Hi, Dr. Josh Wurman, I have an IMAX camera. I have an IMAX camera. Can I go chase with you guys?" He said, "Yeah, sure. Come on out." And little did he know that I'd be a thorn in his side for the next 12 years.
Do you plan on updating the CSWR website, like adding more information about projects and kind of making it more user friendly? Because it needs some updating, is what I should say.
Well, we have all kinds of plans to do it, and the problem is it never winds up being our first priority. I'm going to it right now, and hey, we have something updated there. Somebody put something called Blown Under there, which is a small little project we did last winter. Yes, we always want to do it. We actually have a whole new design. It turns out two of my daughters were very good. One of them does computer science, and the other one, has a computer science degree, and the other one works on digital media for various campaigns. And so I got them as volunteers to come up with a whole new website design, and we had one, and that was 2 years ago, and we never activated it. And we keep saying we're going to do it, and it's just been slow. So yes, I know we need to update it. I know it's kind of primitive and just never our highest priority. My highest priority
I understand that.
my highest priority the last couple of weeks was getting a paper out, and then it's preparing for another mission or updating our data. We've updated our ways of getting data. Other scientists need to access our data, so our archives and getting data and things like that are updated more than these public-facing web pages. One of the things is CSWR. We don't really market ourselves. We're not selling anything to the public. We're not selling ads. We're not doing things like this. So that's why it winds up being lower priority, just because there's just lower motivation.
And lastly, do you have any advice for future meteorologists planning to get in your field of work?
Future meteorologists. Well, if you want to be a meteorologist, I have very old-fashioned sounding advice. It's, do well in school, take lots of math and science. That's a lot of it. The key, the richness of options that you have in a meteorology career depends on having a good education. And not everybody has to go through and get PhDs or master's degrees, but you want a good, solid science, math education, and some specializing meteorology in that. So just focus on that, and you'll be able to understand it's all about data, and it's all about modeling and programming and things like that. The modern world of meteorology, it's a science. So I think your options are much richer if you can do that. Get a good science and math, STEM type education. Kind of straightforward kind of knowledge. Obviously, if you're committed to meteorology. But by getting a good science and math education, there's a lot of different things you can do within meteorology too. There's a few people who are researchers like myself, but there are a lot of people who do forecasting. There's people who work in industry looking at how meteorology and climate affects either future tomorrow's orange prices or whether you're going to build more ships for in the 10-year time frame and climate change and things like that. So there's a huge range within meteorology that can be interesting. So find something that's interesting, I would say. I was talking earlier about how, for me, it's kind of fun. I can build things, and I can also go out and look at meteorology and see new things. So I've been at my most successful when I'm excited about what I do. And I think that's true for most people. Just find either within meteorology some niche that really excites you, or find something related to meteorology. There's things related that are very interesting too.
All right, I think that's it. Thank you very much for taking your time and telling us about these questions.
Sure, great talking to you.
Yeah, great talking to you too. Bye.
How do I? He's kind of there.